For years, the golden rule of AI development has been frustratingly simple, right? Whoever has the most compute wins.
Right. The brute force approach.
Exactly. There's this underlying assumption in the industry that to build state-of-the-art artificial intelligence, you need to be this, like, absolute Goliath.
Yeah, you need the massive, sprawling data centers.
Right. Billions of dollars in funding, just endless GPUs, and a data pipeline so immense, it's almost incomprehensible to normal people.
It really is.
We've just been conditioned to believe that frontier AI is strictly an industrial-scale game, played completely behind closed doors. But today we're going to look at a piece of research that honestly completely shatters that assumption.
It really does. It flips the whole script.
Yeah. So for this deep dive, we are exploring a brand new state-of-the-art technical report from May 2026. It's called OpenSeeker V2, pushing the limits of search agents with informative and high-difficulty trajectories.
It's a genuinely critical paper and, sourced entirely from a team of researchers at Shanghai Jiaotong University.
Just a purely academic team.
Exactly. And what they have accomplished here fundamentally challenges that closed-door, high-compute mentality of, well, frontier AI development.
It totally does. So our mission for you today is to understand how this academic team managed to beat the massive multi-billion-dollar tech giants at their own game.
Yeah, creating AI search agents.
Right. And they did it using a method that is honestly counterintuitive, highly efficient, and a bit of a masterclass in data curation.
It's brilliant. And to really grasp what they've achieved here, I actually want you to visualize something for a moment.
Okay, let's hear it.
Imagine this massive, intricate web of data points just suspended in the air. Thousands of glowing nodes, all connected by these intersecting lines.
Okay, I'm picturing it.
This web represents the incredibly complex search trajectories, like the paths of reasoning, the searching, hitting dead ends, the decision-making, that an AI agent has to navigate to answer a truly difficult, multi-layered question.
So it's not a straight line, it's a whole tangled web.
Exactly. Keep that web in mind, because that structure is basically the backdrop for everything we are going to dissect today.
Okay, let's unpack this. Because to fully appreciate the disruption OpenSeeker V2 represents, we have to talk about the massive barrier to entry that it just broke through.
Right. The resource trap.
Yeah. For you listeners who track AI development, you know that building a high-performance LLM search agent right now is not a simple task. I mean, the industry standard relies on this incredibly heavy multi-stage pipeline.
It's a huge lift. When industrial labs train a frontier agent, they use a highly resource-intensive recipe. Obviously, you have the initial pre-training on just vast oceans of text.
A foundation.
Right. But to make it a capable agent, they then push it through continual pre-training, or CPT.
And that's to ingest massive new corpora of specific knowledge, right?
Exactly. Then comes supervised fine-tuning SFT, where the model is shown high-quality examples of the exact behavior they want. And finally, they deploy complex reinforcement learning, or RL.
And RL is really the compute killer, isn't it?
Oh, absolutely. It's brutal.
It's this massive trial and error process. The model tries thousands of different actions, gets rewarded for good ones, penalized for bad ones, over like millions of iterations.
Yeah, over and over at scale.
It sounds like the industry is putting these AI models through an ultra-expensive, multi-stage Olympic training camp that only billionaires can afford to run. You've got the general conditioning, the specific skill drills, the supervised scrimmages, and then this massive reinforcement phase where it just grinds out reps.
That Olympic training camp analogy is spot on. Reinforcement learning specifically is notoriously fragile and, as you said, computationally brutal.
Just incredibly expensive.
Yeah, you have to run the model, evaluate the output, update the weights, and do it over and over. And the consequence of this, why this matters to you, is that this heavy reliance on immense computing power has erected a massive wall in the AI space.
It's locked everybody else out.
Exactly. It has effectively locked out the open source community and academic institutions from innovating at the cutting edge of deep search capabilities.
Because if you can't afford the compute to run a massive RL pipeline,
you simply cannot play the game.
Right. Which is exactly why the Shanghai Jiaotong University team had to rethink the architecture from the ground up. I mean, they couldn't afford that multi-stage Olympic training camp.
They didn't have the billionaire budget.
So they shifted the focus entirely. They focused on the quality of the practice, not the quantity.
And their core hypothesis was a direct challenge to the establishment. They basically asked, can we achieve state-of-the-art performance using only the supervised fine-tuning stage?
Just SFT.
Just SFT. Can we completely drop the massive continual pre-training and the wildly expensive reinforcement learning phases and rely purely on SFT?
Okay, before we get into how they pulled that off, we need to look at the specs of the model they built, because this is where the efficiency really starts to show.
Yeah, the numbers are wild.
The underlying model they used is called Qwen330B A3B Thinking 2507. It's a 30 billion parameter model. But crucially, only 3 billion of those parameters are active during any given inference.
Which is an incredibly important detail. It means they're using a mixture of experts or MoE architecture. So
Right.
instead of, firing up the entire 30 billion parameter neural network for every single word it generates, it only activates the specific 3 billion parameter pathways.
The experts.
Exactly, the experts that are actually relevant to the immediate task. It makes the model highly efficient to run.
Right, but here's the part of the paper that literally made me stop reading and reread the paragraph. To train this model to become a state-of-the-art search agent, they didn't use millions of trajectories.
Not even close.
They used a highly condensed data set of merely 10,600 data points.
Just 10.6K samples. It's almost nothing in AI terms.
I mean, I have to push back on this a little bit because it feels mathematically contradictory to everything we understand about agentic training.
Sure, it sounds impossible.
Because we both know that SFT is traditionally used as behavioral cloning. It teaches the model the format and the style of a good answer.
Right, it mimics the good behavior.
But reinforcement learning is what actually teaches it to think, to explore, and to correct its own mistakes through trial and error. So wait, how is that mathematically possible? How can dropping the heavy RL and CPT stages and using a tiny data set of 10K samples possibly compete with the heavyweights?
What's fascinating here is that you are right about standard SFT. If you just feed an AI 10,000 straightforward question and answer pairs, it just learns to mimic the answers.
It just becomes a parrot.
Exactly, a parrot. But the secret of OpenSeeker v2 isn't in the volume of the data. It's in the extreme difficulty and the structural richness of those specific trajectories.
So they didn't just give the AI questions.
No, they gave it 10,000 of the most brutal, complex, multi-layered search missions imaginable. And those trajectories inherently included the trial, the error, and the recovery process perfectly modeled out.
Oh, wow. So they baked the reasoning process, including the mistakes and the course corrections, directly into the SFT data itself.
Precisely. If you practice something incredibly complex, something that forces you to navigate dead ends and backtrack, you develop a deep underlying competence.
You're learning the how, not just the what.
Exactly. You learn the overarching logic of problem solving, which then translates to simpler tasks effortlessly.
Okay, so how do you actually build a data set like that? Because if 10,600 data points are doing the heavy lifting of a massive RL pipeline, the architecture of that data must be incredibly specific.
It is very specific, and they outline it clearly.
Yeah, the paper dives into how they modified their data synthesis pipeline to create these ultra-difficult trajectories. And there are 3 distinct modifications at play here. The first one, they messed with the spatial awareness of the AI during training. The researchers call it scaling the topological graph size.
Right.
What does that actually mean in practice?
Well, think back to that glowing web of data nodes I asked you to visualize earlier.
The big tangled web.
Yeah. When researchers typically generate synthetic questions to train an AI, they look at a small, localized cluster of information, a tight subgraph. For example, a single Wikipedia page, and maybe one linked article.
So it's very contained.
Very contained. But what the OpenSeeker v2 team did was intentionally scale up that topological graph size during the data generation phase. They drastically expanded the search perimeter.
So the generated questions require evidence aggregation over multiple nodes rather than relying on a few sources.
Exactly. By forcing a wider topology, the agent couldn't just find one source, extract a paragraph, and be done.
It had to jump around.
It had to retrieve a piece of data from one node, use that context to search for a completely different node, pull data from there, and synthesize them together.
So instead of giving the AI a single sticky note to read, you're giving it a massive detective's conspiracy board.
Yes.
With the red string connecting dozens of seemingly unrelated clues, forcing it to follow the string from one side of the board to the other, cross-referencing as it goes.
That is a perfect way to visualize it. You are mandating deep, multi-hop exploration. But of course, a wider net requires better tools to navigate it, right?
Right. You can't ask an agent to traverse a massive conspiracy board if it only knows how to do a basic keyword search.
Exactly. Which leads right into their second major modification. They significantly expanded the tool set available to the agent. Now they are operating on the React paradigm.
And React stands for reasoning plus acting, right?
Yes, it's a continuous loop. The agent thinks, I need to find X. Then it takes an action to find it, observes the result, reasons about that near information, and decides on its next action.
So it's a much more dynamic process.
Right. And in their previous version, OpenSeeker v1, the agent had a relatively limited set of actions it could take. For version 2, they increased the versatility of those interactions to handle functionally richer queries in that multi-step loop.
What kind of tools are we talking about here? Are we just talking about like hitting a search button?
Oh, it goes much deeper than that. We are talking about the granular actions of real web navigation. Issuing a search query, sure, but also clicking specific links, scrolling down a page to find buried text.
Oh, wow. Actual scrolling.
Yeah, and hitting the back button when a link is a dead end or a hallucination. Or perhaps running a Python script to parse data. By expanding this toolset, they allowed the agent to develop much more complex interaction patterns.
Because it has more levers to pull when it encounters an obstacle.
Exactly.
So you have a massive topological graph of information to search through, and you have a complex set of tools to navigate it. But even with a big board and good tools, you could still ask the AI relatively simple questions.
You could, yes.
Which brings us to the third modification. And honestly, this is the one that really challenges the current industry dogma. They implemented a strict, low-step filtering process.
Yeah, they basically threw out the easy questions.
They essentially looked at their synthesized training data and just started throwing it away. In an era where tech companies are hoarding every single scrap of data they can scrape from the internet, this team looked at successful search trajectories and intentionally discarded them if they were too easy.
They did. Any trajectory that could be solved in too few tool calls was discarded.
Let's define easy here, because this is wild. In the paper, there's a graph titled Tool Call Distribution. And for you listening, a tool call is every single time the AI has to take an action, searching, clicking, scrolling, going back.
Right. Any distinct action.
Any search trajectory in their training data that was a relatively direct lookup or like a shallow two-hop keyword match was completely purged from the dataset.
They established a strict minimum difficulty floor. And if you look at that graph, OpenSeeker v2 allows the agent to make up to 200 tool calls for a single trajectory.
Up to 200. And the average is what really exposes how dense this dataset is. The average steps per trajectory for their 10,600 training samples is a staggering 64.67 steps.
It's unbelievable.
To contextualize that, OpenSeeker v1 averaged about 47 steps, and a competing model mentioned in the paper called RedSearcher averaged only 36 steps. OpenSeeker v2 is routinely executing these massive 65-step deep dives just to answer a single training question.
Let's just think about what a 65-step search actually looks like in practice. It means the AI is querying a search engine, clicking a link, reading a document, realizing the document references a specific policy from 4 years ago.
And then going back.
Right, going back, searching for that specific policy, finding a PDF, scrolling to page 40, extracting a metric, reasoning that this metric conflicts with the initial document, and running a third search to resolve the discrepancy. It is doing this over and over.
It's an incredible test of context window memory and state tracking. I mean, the model has to remember why it started the search 50 steps ago.
Exactly. If we connect this to the bigger picture, you start to see the genius of this approach and why it replaces reinforcement learning.
Yeah, it forces a different kind of learning.
Right. If a model trains on millions of easy two-step data points, its probability distribution naturally collapses towards short-circuiting complex problems. It gets lazy. It expects the answer to be right there.
But this strict minimum difficulty floor changes that.
Totally. By strictly enforcing this 64-step average, they are forcing the agent to learn sustained, long-horizon reasoning. It learns resilience. It builds an internal stamina that you simply cannot get by answering millions of simple trivia questions.
I like to think of it like physical training, right? It's the difference between doing 10,000 jumping jacks and doing 10,000 ultra-complex gymnastics routines.
That's a great comparison.
Sure, both are 10,000 reps. But the latter builds a fundamentally different kind of muscle. The gymnastics routine requires balance, spatial awareness, recovery from a slight stumble, chaining movements together. You don't need a million jumping jacks if you can master the complex routine.
That is a perfect encapsulation of the SFT-only strategy.
But of course, a theory is only as good as its execution, right? You can train a model on 65-step trajectories all day, but if it hallucinates or gets lost in the weeds during actual deployment, it's totally useless.
Right, the proof is in the benchmark testing.
Exactly. The real test is how it performs against the industry giants on standardized benchmarks.
And this is where the academic hypothesis goes up against the industrial reality. They put OpenSeeker v2 through a gauntlet of 5 incredibly challenging agentic benchmarks.
Here's where it gets really interesting. I want to avoid just reading a wall of numbers, but we have a look at the scorecard, because OpenSeeker v2 achieved new state-of-the-art performance for 30 billion-sized React agents across the board.
It shattered the benchmarks.
It did. Let's look at one benchmark in particular that stands out. Humanities Last Exam, or HLE.
HLE is a fascinating benchmark, and honestly, the dramatic name is entirely earned.
It sounds like a sci-fi movie.
It really does, but this isn't a benchmark that asks, who won the World Series in 1998. It is composed of graduate-level, multidisciplinary questions that require deep synthesis.
So it's incredibly tough.
Oh, yeah. You cannot answer an HLE question without traversing multiple domains of knowledge and engaging in rigorous, multi-step logic. It is designed to be the absolute ceiling of what current AI can handle.
Right. And OpenSeeker v2 scored 34.6% on Humanities Last Exam, which, to a layperson, might sound like a failing grade, right? But in the context of frontier AI testing, 34% on HLE is an incredible achievement.
It's massive.
And to prove that, we have to compare it to the Goliath. Let's look at Alibaba's Tangi Deep Research model.
Tangi Deep Research is a highly respected model, and crucially, it was trained using that massive, expensive, multi-stage pipeline we discussed at the beginning, CPT plus SFT, plus intense reinforcement learning.
Yet OpenSeeker v2 decisively beat it. Tangi only scored 32.9% on Humanities Last Exam, and on another benchmark called BrowseComp, which tests complex web navigation, OpenSeeker hit 46.0%, while Tangi maxed out lower.
And even on BrowseComp ZH, the Chinese version, OpenSeeker hit 58.1%. On XBench, it got 78.0%.
It's wild. The 30 billion parameter model, trained on just 10,000 data points, beat the industrial heavyweight on all metrics.
And the paper shows it wasn't a fluke. OpenSeeker v2 also outperformed massive open source models that are exponentially larger in scale.
Like what?
Well, DeepSeek v3.1, for instance, which operates with 671 billion parameters, and GLM 4.6, which runs on 357 billion parameters.
Wait, it beat a 671 billion parameter model?
Yes. OpenSeeker v2, with its highly efficient MOE architecture and tiny training set, is going toe-to-toe with models 10 to 20 times its size. It even outperformed closed-source proprietary models like Claude 4.5 Sonnet on these complex search benchmarks.
That is just... It proves, mathematically and practically, that data quality, extreme difficulty, and structural richness can completely override the need for massive brute force computing pipelines.
It really does.
The AI didn't become profoundly intelligent because it was fed the entire internet. It became intelligent because it was given 10,600 of the hardest exams imaginable and forced to show its work, step by step, across 64 tool calls per question.
And there's a secondary victory here that we absolutely cannot overlook.
Oh.
If you look at the first page of the technical report, you see the logos for Hugging Face and GitHub.
Yes, the democratization aspect.
Exactly. The OpenSeeker v2 model, weights, the code, the entire methodology, it is all fully open sourced for the community.
They didn't just prove the giants could be beaten, they published the exact blueprints for how to do it.
It is a massive win for the democratization of artificial intelligence. It ensures that the academic community, independent developers, and smaller startups aren't just relegated to being spectators in the AI revolution.
They actually have a seat at the table now.
They do. They now have a highly efficient, incredibly capable baseline model and training methodology to build upon without needing to secure hundreds of millions of dollars in compute funding just to get through a reinforcement learning phase.
So what does this all mean? We have dug deep into topological graphs, mixture of experts architecture, and 64-step React loops. But what is the core takeaway for you, the listener, as you process this shift in the tech landscape?
It's a big shift.
I think it boils down to this. OpenSeeker v2 is the definitive proof that data quality, difficulty, and richness can completely override the need for massive, brute force computing pipelines. A purely academic team has democratized frontier search agents.
And honestly, that philosophy extends far beyond the mechanics of artificial intelligence.
How so?
Well, whether you are building an AI model, preparing for a massive project at work, or just trying to learn a new skill, this proves that deliberately practicing high difficulty, complex tasks is far more valuable than mindlessly repeating simple ones.
Oh, absolutely.
True growth happens in the friction of those 65-step deep dives, not in the easy two-step lookups.
It's about intentionally throwing out the easy data, because it doesn't push you to evolve.
Exactly, and this raises an important question, one that isn't directly answered in the text of the report, but it's something to think about.
Lay it on us.
If a tiny team with 10,000 highly difficult data points can rival the output of billions of dollars in computing power, what happens when this quality over quantity philosophy is applied to the very foundation models themselves?
Oh, wow.
Are we entering an era where the smartest AI isn't the one with the most data, but the one that was given the hardest tests?
That is a phenomenal thought to leave on. The era of brute force compute might truly be making way for the era of extreme curation. We want to thank you so much for joining us on this deep dive into OpenSeeker V2. Until next time, keep looking for those high difficulty trajectories and keep questioning the assumptions. Take care.